Let's look at this question, rapid fire question. Van 't Hoff factor for a dilute aqueous solution of strong electrolyte barium hydroxide. The question was to test whether you know the molecular formula of the barium hydroxide or not. That's it. So yes, when we talk about barium hydroxide, you're going to get barium 2 plus and 2 OH minus. Since it's mentioned strong electrolyte, we'll take alpha equal to 1. So I is equal to the number of ions dissociated, which is 3. So D becomes the answer to this question. Very simple. So what do you have to do in this question? Again, I is equal to 1 plus N minus 1 alpha. I, we have 2.74 in the question. Barium nitrate, again 3 minus 1 alpha. So we just need to solve 1.74 divided by 2 will give us the answer. So it will be, and you can just, because you have to find percentage of dissociation, you know that you just multiply by the 100 and you will get the percentage dissociation. So 174 divided by 2% will be your answer. That means 87%. B becomes the answer to this question. So we have done questions related to alpha as well as the percentage dissociation. And you know the relation. All that you need to do is multiply alpha with 100 and you get the percentage, right? Question says the vapor pressure of pure benzene at a certain temperature is 0.850. So this is your pure P naught A, which is equal to 0.850. A non-volatile electrolyte solid weight of the solute is 0.5 grams, is added to weight of the solvent 39 grams. The molecular mass is also given of the solvent 98 gram per mole. Vapor pressure of the solution then is, so PS is also given equal to 0.845. What is the approximate molecular mass? We'll make use of not the formula of the colligative property, but the modified formula. What is the modified formula? We just learned P naught A minus PS by PS is equal to WB by molecular mass of B into WA by molecular mass of A. All we need to do is substitute the values. Let's do that. P naught A 0.850, PS 0.845. That gives us in numerator 0.005. Divided by PS is 0.845. Let's just write it like this. 0.845 is equal to WB. WB is given to us as 0.5. Molecular mass of the B, that's what we need to find out. Molecular mass of A, 98. Weight of A, 39. Let's just solve whatever we can. So the 39 into 2 is 98. This we have taken care of. Let's just get rid of the decimals. 1 here. 1, 5, 6, 7, 8, 34. So 6, 45, 169. Okay. So molecular mass will be equal to, let's just take 0.5. Look at this. You'll see that the calculations will be a little haywire if you're going to put that other formula. But here molecular mass will be equal to, so 169 into 0.5 into 2. Are we missing on anything? I hope not. This goes here, 0.5 into 2 into this is equal to 1. So 169 approximately 170 U becomes the answer. So we will get answer as option C, but you can try doing it with the normal method. You will see you'll have a very hard time. So correct. So 169, the closest answer is 170. So C becomes the answer to this question. Correct? Okay. Now, henceforth, it is important to make use of this particular modified formula. But there will be times when the examiner might write that the moles of the solvent are more than the moles of the solute. The purpose for writing that formula, that statement, what am I saying? Listen to this very carefully because it can be game changer. Most of the questions will be dealt in this modified formula. But if this examiner is writing explicit, wait for the explicit writing that the moles of the solvent are way greater than the moles of the solute. In that case, we know that NB divided by NB plus NA is equal to P naught A minus PS divided by P naught A. And this examiner wants you to take equal to the NA. In that case, make use of the relative lowering of vapor pressure formula only. Because this will create difference. If you're not going to take P naught A, but you take PS, your answer will come out wrong. The examiner has given you this data so that you use the same colligative property formula. Will you be mindful about it? That will be a game changer if you do not address this very important statement. Okay. In this question, you will see that if we make use of the formula that I just explained, which is going to make our life easy for the relative lowering, the actual formula we know is P naught A minus PS by P naught A is equal to XB. But I'm not going to make use of this formula. I'm rather going to make use of P naught A minus PS by PS is equal to NB by NA. So we know that what has been given, that the vapor pressure is 2% less than the vapor pressure of the pure water. So this is 2 by 100 of P naught A, right? That is your P naught A minus 2 by 100 divided by the PS, which is, again, we can write 2% less than the vapor pressure of the pure solvent A. So if the pure solvent A was P naught A minus 2 by 100 of the P naught A, that is the pressure of the solution, which comes out to be 98 by 100 P naught A. So this is your PS. So that is what that goes wrong. Sometimes we just do this. This is actually ulta. So let me write it by keeping, it's not saying that the percentage is 2%. It is 2% less than the vapor pressure of the pure water. So I've also shown you what might go wrong. So keep that in mind. Read the language of the question carefully. So P naught A, let's say, is P naught A minus 0.98 P naught A divided by 100. I've already taken care of by writing 0.98 divided by 0.98. So you're getting 0.02 divided by 0.98 equal to, you have to find out the weight of the urea divided by 60 into the weight of the solvent already given to us 400, and we know the molar mass 18. So W will be equal to 0.02 into 60 into 400 divided by 0.98 into 18. Correct? The values are quite far away, so some approximation will not be harmful for us. Let's get rid of the decimals. Okay, 98 is here. Let's just consider it 100 and get rid of the zeros. Now you have 18, so 9 here and 2 here. You have 60, so 3 here, 20 here. So 2 into 2 into 2, 8. 4 into 2, 8. So you can see that 80 divided by 3 approximately will be your answer. That means 6, 7, 8 to 26 point something should be your answer. The closest answer is option B. So we'll go with option B as our answer. Now you try doing it using this formula and you will know why I have taught you this formula. Okay, but this is not relative lowering in vapor pressure. This is only for the calculation purposes. I hope this point is well clear now. You can see that in this question, what you have to do, you have 100 degrees Celsius vapor pressure of a solution of 6.5 gram of the solute. So 6.5 gram is the solute molality we have to find, right? Molar mass of the solute, do we have? No. Where do we get the molar mass from? Rather than getting the molar mass, do not wait for it through the molar, that we'll find the molar mass and then come to the mole. Find the moles from relative lowering of vapor pressure. And from the moles of the solute using relative lowering of vapor pressure, you can just directly solve this question, that delta TB is equal to KBM. M here will be NB divided by the weight of the solvent in kg, which is given to us. This is given to us 100 gram of the water. Great. This is also given to us. KB is 0.52. Delta TB, the boiling point of the solution will be, so delta TB is what? We have understood that temperature of the solution will be greater than the temperature of the pure solvent. The boiling point of the solution will be greater than the pure solvent. This we know is 100. This we need to find out, right? This we know we can find out from relative lowering of vapor pressure. How? Because you have been given 6.5 gram. This is 732 mm. So 760 minus 732 divided by 760 P naught A, but we'll take it as PS only. So we'll take it equal to 732 only to use the modified formula and not the relative lowering of vapor pressure formula. is equal to NB, this we wanted to know, divided by NA. NA is going to be what? 100 divided by 80. This is going to be equal to, or let's just not solve it. So what is your NB coming out to be? Can you find out? This is 28 divided by 732. This goes here into 18 by 100. Can you find out what is the NB, which is coming out to be equal to? 0.212. Great. So NB is coming out to be 0.2 approximately. So this, if I know from the relative lowering of vapor pressure, 0.2 into 0.5 basically, do you understand, is going to be 1 by 10, right? So this is just to be kept in mind. These calculations are pretty simple now. 0.2 divided by 100 into 1000, because we have to have the weight in the kgs. So you can get rid of the decimals here. 100 here, 10 here, 1000 gone, 52. So 4, 10, 104 approximately, so 1.04. So when you take TS, you have to add 100. So 100 plus 1.04 approximately will give you option C as the answer. 101 degree approximately will be the answer to this question. Okay, so what was interesting is now the collaboration between the relative lowering of vapor pressure and your elevation and boiling point, two colligative properties that we are using together. Is it fine? All set? Again, let's see this question. This question seems to have simple calculations. We have 0.15 gram of the solute. Okay, let's just keep writing whatever we have. WB is 0.15 gram dissolved in the 15 gram of the solvent, boiled to the temperature higher by, so delta TB actually is given to you already, right? Then that of the pure solvent. Molecular weight you have to find out. The KB is given to you as 2.16. So 0.216 is equal to 2.16. You can see the calculations are going to be easy for us. 0.15 divided by 15 divided by molar mass into 1000. Let's get rid of the decimals. So 100 here. Let's get rid of the decimal. 1000 here, 100 here. Let's see what all cancels out. So 1, 2, 3 zeros are out. 1 0 is out from here. 216 tata bye bye. 15 tata bye bye. Molecular mass is going to be equal to 100. So this is what we've got. Any objection? So B becomes the answer to this question. I hope everybody could do it. Simple one. Rapid fire, 15 seconds for you. Very simple question. I'm not giving you time. Just read it and let me know the answer to this question now. 68%. This was a very simple question. Please, no, don't change KF with concentrations. It doesn't change. Be it 1 molar if I take 2 molar for water. And it depends on the solvent. The KB and the KF depends on the solvent, mind you. We're deciding, I told you 0.51 is for the water, which you should remember only the KB value, right? So always keep in mind that these kind of constants don't change with the concentration. They would only change with the temperature. They would only change with the solvent. So not even with the temperature, they would just change the constants, the KB and the KF. They will change just with respect to the nature of the solvent, nothing else. Okay, so they remain unchanged, be it KF or KB I talk about, they remain unchanged. So the answer is option C for this question. All right, it was a simple question to do it. So very quickly, let me give you the solution, KFM. So KF value, already you have it, 5.12, and molality, you have everything for the molality, you had to just multiply, and that would have given you delta TF. And option B is the right answer to this question. Okay. Okay, time to see the leaderboard. So this question, if you remember the molar elevation constant, it is 0.51 degrees Celsius or Kelvin kg per mole. Nothing changes. So you should remember it, but you can find it out easily. So I'm not going to post a poll for you. You can do it properly also, but since the values are quite away from each other, or if you do not remember, you should solve it. That delta TB is equal to KBM. So delta TB, you already have out here that 0.170 degrees Celsius of elevation. So 0.17 kb we need to find out, molality 0.45 gram of the urea with the molar mass 60 in 22.5 gram of water into 1000. This will give you result as 0.51 degrees Celsius kg per mole. Okay, simple one. Let's move ahead. All right. So how to deal with such a question when you have which of the following aqueous solution has minimum freezing point? Whichever will be having the highest amount of the solute, that will have the minimum freezing point. So you can try this question. You can figure out of all, this is the one, 0.01 into 2, giving you 0.02 is the maximum amount of solute that we are having. Rest all will be less. So A becomes the answer to this final question of the day. So please check this question. Note down whatever is given to you. The moles are given to you. The volume is given to you where it ionizes to give X2 plus and Y2 minus. The observed osmotic pressure is 3 atm. Molar mass of X is 24 and Y is 32. Find the observed molar mass plus 2I. This is interesting. This makes this question very interesting. So do not be in a haste to just answer the molecular mass. You just don't have to find out the molecular mass. And it is about osmotic pressure. And we now know that osmotic pressure is brilliant for finding out the molecular masses. But we also have to add 2I where M observed is observed molecular mass of the XY2. Okay, so we have to find the observed molecular mass. Let's see the formula that we already know. So here you go. XY2 giving you X2 plus Y2 2 minus. We know pi is equal to ICRT. Pi's osmotic pressure is given to us as 3. Please check. This is where it is given. The osmotic pressure is 3 atm. Okay, so pi we have substituted. I we do not know. Right? Okay, what else we know? We know the moles. CRT. What is C? Concentration is molarity. Moles per unit volume. Okay, so 2 liter. We know the volume also is dissolved in 2 liter. Okay, so 0.1 by 2. We know the molarity. R, thank God, examiner has helped us a big time by giving us the value of R. This, in fact, you can remember that you can take, instead of taking 0.0821, you can simply take 1 by 12. Okay, so here you go. This is what is given to you. Temperature is also given to you. Where is it? 87 degrees Celsius. When you convert it into Kelvin, what do you get? 360 Kelvin. And you know the OG formula, the very important formula, I is equal to the molecular mass calculated divided by the molecular mass observed. When it is about the colligative property, it is a colligative property observed by colligative property, which is calculated. But you know that in all of them, the molecular formula, molecular mass lies in the denominator. Hence, while writing the molecular masses, it's opposite. Never do it wrong. You can remember this. And from there, you can remember the formula of the molecular mass, that what we have is the calculated in the denominator, what we have is calculated in the numerator and observed in the denominator. This is what we have to find out. So this will be equal to, now I, what will be I? We figured it out from here. Check, we can just solve it and get our I. What is our I coming out to be? Let's just solve. Let's just get rid of the decimal. 0, 0 gone, 1 here. We have 1 here and 8 here. Please check. I'm just solving it. Okay. And we have 12, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 4, 6. Now you can see we can just solve this also. 1 here, 2 here, 1 here, 2 here. So the I comes out to be 2. Simple calculations. We have substituted molar mass calculated divided by 2. What is molar mass calculated? What do we have? Please check. It is ionizing and X is this and Y is this, but what we have is Y2. So don't forget to multiply 32 with 2 so that the molar mass calculated that we get from here is going to be equal to 88. So 88 by 2, that means 44. Now that's your molecular mass. Do not be in a haste to answer this. If this was one of the options, you will be very tempted to mark it. Do not forget there is also plus 2I. So plus 2 into I, which was 2. So 4. So 44 plus 4, that means 48 becomes the right answer for this very interesting question. I hope it is clear. No objection. So 48, where are you? Option C becomes the right answer to this question. Okay.